So now we'll see. Will it be attracted to or repelled? It's repelled. So using the positive glass rod, I was able to give the ball a negative charge. At least some of you watching the video are probably pretty confused right now. How on earth, using a positively charged glass rod, did I wind up making a metal ball negatively charged? You may have thought, well, put that positive charge near it, you're going to transfer a positive charge over to it. Some of you may have had some idea of grounding. You might have heard of grounding things before and might realize, oh, when I touched it with my finger, I was grounding it. And maybe you might think that means it would have to be neutral at the end of all this. So let's go through the argument and see how the charge model explains how I made the ball negatively charged. So here we go. Here's our neutrally charged metal ball. Here's our positively charged glass rod. I've just made some copies down here so I can make a sequence of diagrams. And let's think about what happens. So I put the rod close, but not touching. And I think, hopefully, you know what that does. The negative charges in here are going to tend to be attracted. We're going to polarize the ball. This actually isn't all that important for the process we're about to talk about, but I'm going to draw it anyway because that's what would happen. All right, let's think about what happens next. So here we are. We've got our polarized metal ball, and I touch it. And the way I'm going to draw that, I'm going to draw a very strange picture of myself. Here's my picture of myself. That's a pretty good self-portrait, right? I look just like that. Well, no. What I've just drawn is the symbol for grounding. I have grounded the ball. I have connected it to the earth. Why? Why is that important? Well, I'm actually a pretty good conductor. So are you, by the way. And the Earth is a great big source of charge. It's more or less neutral. And so there's a lot of charge out here in the Earth that's available for us to move around. So this is me. That's the grounding symbol. And this bunch of pluses and minuses, that's the Earth. I hope you're impressed with my artistry. All right, now what happens? Look. The ball has this positive charge near it. And so negative charges are going to tend to be attracted into the ball. So we're going to tend to get some of these negative charges flowing up through me and out of me and onto the ball. So what we're going to wind up with is that now the ball is somewhat negatively charged. It's still connected through me to ground. Okay, and so we still have a whole lot of charge available down here. But the point is now, remember, I remove my finger first. So I cut this connection. Now all that excess negative charge on the ball is trapped there. It can't get off. And all I have to do now is quickly move the rod away because this ball is going to be rather strongly attracted to it and it's going to tend to come and whack it and transfer all that negative off. And so if I want this to wind up negative, I've got to move that rod away quickly. And there we have it. The ball is now negatively charged. Effectively, what we've done is we've connected the ball to a source of charge. The Earth is our source of charge. And then, while it's connected, we've used this positively charged rod to pull negative charge up onto the ball. And then we cut the connection so it's trapped there. And this whole process is called charging by induction. And in fact, many of you have probably seen this in high school, and if you're like most students, you actually didn't understand it. So hopefully now, with a little bit more understanding of a charge model, this might be making more sense to you. The point is, this shows that using charges, we can use them to push and pull on other charges to cause separation of charge and make other things be charged in different ways without touching them, just by pushing and pulling on charges. Last bit of this lecture is about the view of charge on the atomic level, because to understand some of the things that we'll see later on in the course, you sort of need to understand this. Now, a lot of this you will have seen. Here's a picture of an atom. Well, no. Atoms look nothing like this. In fact, we can't draw pictures of atoms. So this is not a picture of an atom. This is a picture of an idea of an atom. But the important parts of the idea are that the positive charge is all in the nucleus, in the protons. There are also neutrons in the nucleus. They're uncharged, and for this course, we really don't care about them. The nuclei are pretty much stuck in solids. They don't move around. What moves around, or could move around, are the electrons. The electrons aren't in the nucleus. They're in a sort of a cloud around the nucleus. And to some extent, they can move around in the solid. And how much they move around in the solid is what determines whether the solid is a conductor or an insulator. One thing to know, and I say it's a handy factoid because it's one of these just little tiny facts, is that the charge on a proton is positive an amount that we call E, which is the fundamental charge unit. The charge of an electron is exactly the same magnitude, but negative. And the value of E I give to 4 sig figs here. It's really not important. Don't remember this. Remember that there is such a thing as a fundamental charge unit, that the proton has a positive fundamental charge unit, an electron has a negative fundamental charge unit. And if you need to know how much charge that is, look it up. This is the 21st century, and you probably have a smartphone. Whether or not an object is a conductor or an insulator is determined by how charge moves around in it. And in solids, that mostly means how electrons move around. So in conductors, such as metals, the important thing to realize is that the electrons aren't really in clouds around individual atoms. They're sort of shared among all the atoms. We could call it a sea of electrons. And so the view that you might want of a metal is that each electron is free to just move around anywhere, and the nuclei are sort of hovering in this sea of electrons. Now, in fact, there are all sorts of things wrong with that picture. It's not just the nuclei, because it's only the valence electrons that are allowed to move around freely. But that's good enough. Insulators are totally different, though. In insulators, the electrons are more or less locked within the atoms or molecules that they belong to. And so they really hardly ever move out. It's very difficult to get them to move out, and that's why charge doesn't flow well in the insulator. Knowing that difference between conductors and insulators, you may realize we need to sort of have another bit of discussion about polarization. The description of polarization I've given you works for conductors, right? You put a charge near the conductor, the electrons move around as a result, and now one side of the conductor is more positive and the other side is more negative. But in an insulator, the electrons can't move around, and this picture doesn't work. So what happens in insulators? Because we know we can polarize insulators, that's why we can pick up bits of paper with charged objects. Well, you can polarize individual atoms as well. So suppose you put an ion. In this case, I've decided to put a negative ion next to an atom. The electron cloud in the atom tends to be repelled away from the ion, so that it's more over on one side of the nucleus. And so now you have a polarized atom, and that atom will be attracted towards the ion. So that's how insulators get polarized. If you put a charge near an insulator, each atom inside the insulator becomes polarized. Now every one of those atoms is attracted towards the charge, and so the insulator as a whole is attracted towards the charge. Final thing I'm going to leave you with in this lecture is just a few things about charging and the process of charging. We started off looking at charging objects by rubbing them, and generally when we're charging insulators, that's how we do it. Conductors are different, and so it's worth understanding a little bit about the differences between insulators and conductors and how they charge. So when we are charging insulators, what's going on is that the insulator is typically made out of molecules. So here's some molecule made out of atoms with bonds connecting them. If you break a bond in the molecule, often it'll break up in such a way that you get two fragments, and often the charge will be unevenly distributed between them, so that one of these fragments is negatively charged and the other is positively charged. You call these molecular ions. Now, if you have two materials, so here's insulator 1 and insulator 2, and I've drawn insulator 1 as being made out of the molecules I was just showing you. Insulator 2, of course, is also made out of molecules, but I'm not bothering to show you them because there's nothing going to happen with them. Now let's say we rub these two insulators together. What can happen when we rub them together is that we cause a bunch of bonds on the surface of this insulator to break. And so we get some of the molecular ions, say the negative ones, left behind on insulator 1, and the positive ones transferred over to insulator 2. But don't think that it's always the positive ones that get transferred. When you're rubbing insulators together, you can get positively charged or negatively charged molecular ions transferred. The transfer can go either way, and in fact there may be a whole lot of different kinds of molecular ions being formed. And this process is basically different for every pair of insulating materials that you rub together. This is very, very complicated, and really it comes down to surface chemistry, because you're modifying molecules on the surface because of their interactions with the other surface that it's rubbing against. Now, in contrast to that, charging conductors is really very simple. Only electrons are free to move around in metals, as we've discussed, and so metals tend to become negative by gaining electrons from something else. When you charge a metal so that it becomes positive, what you've done is you've removed electrons from it, and so the metal is positive as a result because you've taken negative charge out of it. And this is true whether you're charging the metal by direct contact with a charged object or by induction. All you're doing is putting electrons in or taking electrons out of the metal. Simple, right? So you can't charge metals by rubbing. Well, sort of. The thing is, what goes on is that you may well generate charge on the surface of the metal when you rub it. But because charge flows freely through the metal, it'll all just flow away to ground because you're a conductor and so is the conductor that you're rubbing. And so any charge you generate on its surface tends to pretty much instantly just run away to ground. And so this isn't a practical way of charging conductors. Although there are some important cases where this does happen. For example, airplanes with metal skins flying through clouds have a tendency to become charged because of the friction between the water in the clouds and the skin of the plane. And this is important if the planes aren't properly designed to deal with this. The buildup of charge on the plane can disrupt radio communications and cause all sorts of other problems.